In semi-arid farming environments, the success or failure of a crop isn't decided on the surface. It happens below ground, where roots must chase moisture deeper. But when that root stops completely, the crop's potential dies with it. Across the Australian wheat belt, roots run into two distinct invisible walls. Years of heavy machinery use have compressed the dirt into a dense physical plate, while chemical degradation has turned the surrounding soil highly acidic. These are separate biophysical issues, but they stack on top of each other to create an impenetrable zone. The physical compaction stops roots from pushing downward, and the acidity creates a toxic environment that stops them from branching outward. In a severely degraded profile, the metrics are deeply hostile to plant life. At 20 centimeters below the surface, soil strength hits 3.5 megapascals. The pH drops to 4.0. Extractable aluminum reaches highly toxic levels. You can apply heavy doses of surface fertilizers or receive perfect seasonal rainfall. If the root architecture cannot physically penetrate the top layer to access those inputs, the inputs are wasted. To measure exactly how these constraints restrict crop growth, agronomists set up a large-scale field trial in 2018 in Kalannie, Western Australia. The researchers needed to decouple the mechanical resistance of the soil from its chemical toxicity. By isolating the variables, they could find out which factor actually controls planter root length density. They divided the site into 3 test plots. The control plot was left both compacted and acidic. The second plot was mechanically loosened, but left highly acidic. The third plot received mechanical loosening plus a heavy incorporation of agricultural lime to neutralize the acidity. The physical intervention at the site was aggressive. Excavators systematically removed the soil layer by layer down to a depth of 45 centimeters, treated the dirt, and then replaced it. By separating the physical crush of the soil from the chemical burn of the aluminum, they could map the exact numerical thresholds where root systems fail, allowing them to reverse engineer a high-yield soil profile. This regression tree analysis models the Kalannie trial data, showing the exact hierarchy of constraints on root development. The initial split reveals the dominant factor. Root development hits a hard stop when soil strength exceeds 2.6 megapascals, dropping planar root length density down to 18.9. Biologically, this means the root tip simply cannot generate enough force to push deeper. Downward elongation ceases entirely, and the roots are forced to grow sideways. In the control plot, the extreme compaction creates a physical wall so severe that the plant never encounters the deeper chemical toxicity. It is locked out long before the aluminum becomes a factor. Once the soil is mechanically loosened to 45 centimeters, that 2.6 megapascal barrier is broken, and the roots plunge vertically through the soil profile. At this depth, the soil in the loosened plot is still highly acidic and toxic, but the primary roots continue their downward drive anyway. Mechanical impedance dictates root depth. A root must be able to physically move through the dirt before the chemical toxicity even matters. Driving roots deep into the ground provides an immediate physiological payoff for the crop, measured in water uptake. This chart plots soil water content across 4 growth stages. The control treatment, the tall left bars, fails to push deep roots, leaving 15% of the water capacity entirely unused. The 2 engineered plots show a completely different result. During the critical later stages of anthesis and grain fill, their deep roots deplete the water pool, dropping those moisture levels significantly lower. Notice that both the loosening alone and the loosening with lime performed identically here. The severe chemical acidity in the loosened clot did not stop the taproots from extracting moisture. Breaking the physical compaction pan buys the crop access to a hidden subsoil reservoir. The plant solves its immediate water deficit even in toxic dirt. If mechanical loosening successfully secures the water, we have to ask why the plot that was only loosened failed to reach the maximum yield potential. Returning to the regression tree, we see what governs growth after the mechanical barrier drops below 1.2 megapascals. The nodes split again based on pH and extractable aluminum. When soil pH drops below 4.7, highly soluble toxic aluminum attacks the root system, inhibiting cell division and stopping lateral roots from branching outward. To combat this, the third test plot utilized a dual amelioration strategy, injecting agricultural lime deep into the soil, down to the 45-centimeter mark. The lime raises the pH, which neutralizes the aluminum. The chemical sealing that stunts lateral root branching is removed. Under these optimal biophysical conditions, the regression model traces down to a maximum planar root length density peaking at 33. Combining physical loosening with deep lime incorporation resulted in a 75% increase in root density compared to the control treatment. There is a division of labor in soil engineering. Mechanical loosening allows primary roots to travel down, but chemical neutralization allows lateral roots to branch out, transforming a sparse taproot into a dense, absorptive network. That absorptive network determines the actual nutritional payload delivered into the plant tissue. Increased root surface area and fine root hair development are mandatory in poor soils. The plant relies on surface area to physically intercept minerals. Highly mobile resources, like water, can be secured by a few deep roots, but highly immobile resources, like phosphorus and potassium, require a massive network of fine roots sweeping through the entire soil matrix. This chart shows exactly how that translates to nutrient acquisition. When lime was added to the loosened plot, the tissue concentrations of nitrogen, phosphorus, and potassium saw massive spikes compared to the plot that was only loosened. Water acquisition only requires physical access. True chemical fertility requires the intense lateral root proliferation that only chemical amelioration can provide. All of these biophysical data points culminate in the final above-ground grain yield. In the control baseline, locked out of subsoil water and nutrients, the crop yielded 1.33 tons per hectare. Breaking the physical barrier secured water, doubling yield to 2.80. Breaking both barriers secured water and immobile nutrients, maximizing yield at 3.57 tons. Farming degraded semi-arid soils comes down to an absolute programmatic rule. You must break the physical barrier to acquire water, and you must neutralize the chemical barrier to acquire